Good morning, everyone. I hope all of you are doing fine and well. And today we are going to look at into one of the topic which we were touching briefly on, that what is quantum in computers or current processors? Because we know, all of you know, that that is the in computers, when we see that there is quantum in current microprocessors. That is the interesting part, that we heard about, or we hear there is a quantum computing, quantum processors, but do we know that there is quantum inside our current processors also, right? And what it is, that is what we are going to look at today briefly, what it is. So you guessed it right. In the microprocessor, if you see heart of the microprocessor or this computing devices is your MOSFET, right? And this MOSFET, in a very simple sense, we saw that this was silicon on top of some semiconductor. You're putting your oxide, your metal, right? And then you have your source and drain. This is what is the gate, this is your source, this is your drain, and that is your body. Now, the question you will ask, where is the quantum in this, right? Where is quantum? And the question is, what is quantum, right? If we ask where is quantum, then the question is, what is quantum? And that is where we have to go back to the history of where the first relation between, let's say, what we see in the classical domain, right, and the quantum domain. This was established by none other than de Broglie, using a wavelength, where this was the relation which we know as the de Broglie. You say de Broglie, I think, but it's a French name, de Broglie wavelength, right? So what he related is that there is a classical which we treat, let's say, electron, which we were briefly talking in the last video when we were talking about light coming out of semiconductors. Electron can be a particle, right? Particle means it's like a ball, how we treat. There's M, which is defined, there's V, which is defined, right? Obviously, X is defined. And here in this, we can say we are in the world of duality, right? So it's a particle and wave. And that is the thing which is related by this wavelength and the momentum. So basically, momentum, as we discussed, can be mv. So that is what relates this wave property of your electron to this particle property, right? Okay. So that is the basis of what we understand from quantum, that there is a wave and particle duality which is going to come. Now you say, okay, I have this channel. The electron is going from here to here, let's say. And if we assume pockets, then, example, if we assume pockets of n plus 4, let's say this is a p-type transistors, then electron has to travel this length, which is what we know as also the channel length. So now you can say that once my electron is here, right, and it's going there to the other side, it has to cross this LC edge, right, which can be, if we know that if the gate voltage is sufficiently high, in this case, then you will have a channel so that it would go. Now the question remains is, what is quantum, right? Here, can I still treat this electron as a wave? Because we have been treating it as a particle. Can I treat it as a wave? And the answer is, you can always treat it as a wave or particle because it is a quantum mechanical quantity, right? So that is the basis. It's a quantum mechanical entity. So that means that it has to be, in principle, treated as a quantum mechanical entity. But what happens is, when we are evaluating devices, you see that you are not using quantum until it is required. And the reason for that is because, you see, Now you have to ask that yourself a question: when can I treat it as a complete particle, right? When can I omit, or when can I use the classical picture, right? That is the question you're asking, because you're saying that anyway, electron is anyway the quantum mechanical particle. So I cannot really say that, okay, it's not quantum mechanical, it's quantum mechanical. Now the question is that when I'm evaluating devices, when do I really need to use quantum mechanical? When can I get away with the classical? That is the question you're asking. Because classical physics, when we solve, it's much easier to solve and much faster, right? But in quantum mechanics, the things are much gray, in the sense that we go into the world of probabilities and away from the deterministic. So now the question comes, or the answer to for that comes from that when can I use is when my length of whatever I'm looking at is much greater than this lambda, which we are talking about. That is, means the classical picture will hold. Okay. And the simple explanation for that is that your wavelength of the electron, or de Broglie wavelength of the electron, is much smaller compared to the length scale, or the length scale is much bigger. So one can even evaluate this lambda for let's say, because h is a Planck constant, so it can evaluate this lambda for let's say uh, a particle in silicon. Right? Hi. So this is what for silicon, you may find out this comes out to be, let's say, 20 to 30 nanometer, right? The wavelength, I mean. And for silicon, you can find out what is the mass of the electron, what is the velocity, right? Typically. So that means you can find out, okay, this comes out to be, let's say, 20 to 30 nanometer for silicon. Now that gives you in some sense that if I'm using channel lengths, which are much larger than 20 to 30 nanometer, then this is okay that I can use my classical picture, or classical picture of how electron goes from source to drain, right? That is one can use. But suppose if this was not really 20 to 30 nanometer, which is the case in current transistors, where we see LCH is anyway between, let's say, 15 to 20 nanometer. So then classical picture cannot, may not be accurate, right? And then people are probably looking at the different ways to account for, because they do have a setup already for classical picture. So one would not completely get away from that, and would see that how do you implement whatever, let's say, if you see some quantum mechanical feature or quantum mechanical effect, right? This is the how the industry typically works is uh, they see how can this effect be merged into this, right? So how can we add this into this so that we can make it more accurate? So that is the modus operandi of typically the industry, where, but we do see that the quantum mechanics is going to govern these processors, or are governing these processors already, right? Now the question is it a quantum processor? Then can I say no? So the quantum processor, when we define quantum computing, is defined in a very different way, that how we compute. We are still doing whatever we know as the von Neumann, right? Where there is a computing. So that is the still the way we are computing with these transistors, right? Which is what is being challenged as of now. Is this the only way to compute, or are there other ways which can be made available for future computing paradigms, right? So that brings me to this. So I would just end here and probably pick up from here, that because there's so much quantum inside the current processor, this is just one example of where I took that this LCH, if it is compared to lambda, right? How big or small it is, and that gives you that can I treat this electron as a, or would the classical picture hold here or not, right? But there is other quantum. There are a lot of quantum in this device itself, which we are going to see in the next video. Thank you, and keep learning, keep growing, all of you. Bye bye.